When you look up at the sun, do you ever just think about the sheer power up there? It's this giant nuclear reactor in the sky, right? But it feels so far away, and yet somehow we figured out how to grab that sunlight and turn it straight into electricity. It really does sound like something out of a sci-fi movie.
I mean, really think about it. There are no wires stretching across space, no fuel being shipped, not a single moving part, just this silent, solid panel that sits there soaking up the sun, and out comes electricity. It's just so simple, so elegant. It's one of the coolest things we've ever come up with.
So, the big question is, how? How in the world does something as, well, intangible as light become the power that runs our lives? How does a beam of light, after traveling 93 million miles, turn into the juice that charges your phone? All right, let's get into it. This is where it gets really fascinating.
Okay, to really get how this magic trick works, we've got to start with the messenger itself. We need to talk about what light actually is.
You see, light isn't just some glow. It's actually a stream of these tiny individual packets of energy, and we call them photons. Think of sunlight less like a wave in the ocean and more like a constant downpour of these little energy bullets. They're what's zipping through space from the sun to us.
And here's the wild part. Each one of these photons is carrying a specific punch of energy. It has momentum, so when it hits something, it's not just a gentle tap, it's an impact. It can actually transfer its energy to whatever it hits. And that little transfer of energy, well, that's the secret to the whole shebang.
All right, so we've got these little energy packets, these photons flying from the sun. So where are they going? Let's zoom right in on their target, the solar panel.
So what's the magic material here? It's silicon. Yep, the same stuff that makes up sand and is at the heart of all our computer chips. And the cool thing is, it's the second most abundant element on Earth, so lucky for us, we've got plenty of it. Now, when you get silicon in its pure crystal form, it's all neat and tidy. The atoms are locked together in this perfect grid. Every electron is tightly held in place, bonded to its neighbors. It's super stable, which is great, but it's terrible for making electricity. Why? Because to have a current, you need electrons that can move. And in pure silicon, they're all locked down. There's no flow.
Okay, so you've got your energy-packed photons from the sun on a collision course with this crystal full of locked-up electrons. So what happens when they finally meet? This is it. This is the moment everything hinges on.
This is the big one. It's called the photoelectric effect. Imagine that photon from the sun just slamming into one of those electrons. It transfers all its energy in that one instant. And if the photon has enough juice, it's like a perfect break shot in pool. Bam! It knocks that electron right out of its spot, sending it free. Now you've got a free electron that can move around, and you've got a little empty spot, a hole where it used to be. And get this. This is the very idea that won Albert Einstein his Nobel Prize. Not relativity, but this. He figured out that it's a one-to-one deal. One photon hits one electron. The photon's energy is first used to break the electron free, and then whatever energy is left over gives that electron a good shove to get it moving. Okay, so we've freed a bunch of electrons. Awesome. But now they're just zipping around randomly inside the silicon, like a chaotic mess. That's not electricity, that's just heat. To get actual useful power, we need to get them all moving in the same direction. We have to create like a one-way highway for electrons. And this is where some seriously clever engineering comes in. What scientists do is they create this kind of silicon sandwich. They take one layer of silicon and they dope it with a little phosphorus. Phosphorus has an extra electron that doesn't fit in, so this layer has a bunch of free electrons ready to go. That's our N-type or negative layer. Then, for the other slice of bread, they use boron, which is missing an electron. This creates a bunch of holes that are basically positive spots. That's our p-type layer.
So what happens when you stick these two layers together? Well, it's instant chemistry. The extra electrons from the N side immediately jump over to fill the empty holes on the p side, right at the border. This little shuffle creates something amazing, a permanent built-in electric field right at that junction. And this field, it's like a super steep slide. Anytime a new electron gets knocked free by a photon, this field grabs it and forces it to slide one way, toward the N side, and it pushes the hole the other way. It's a perfect, automatic, one-way street for electrons.
And that's it. That is literally it. That constant, organized, one-way flow of electrons, that's an electric current. That's the electricity.
We've taken the chaotic energy from sunlight and, through some brilliant physics, channeled it into a perfectly orderly, usable stream of power.
So we've got electricity happening at this tiny, microscopic level. But that's a long way from powering your TV, right? So how do we get that power from the panel and into your house?
Well, it's basically a three-step process. First, you can't get much power from one tiny cell, so they wire dozens of them together to make a full solar panel. This boosts the voltage and current. Second, the panel creates DC, or direct current. Think of the power from a battery. But our homes run on AC, or alternating current. So you need a crucial piece of gear called an inverter. Its only job is to flip that DC into the AC that your home can actually use. And then, step 3, that AC power is good to go. It can run your appliances, charge your car, whatever you need.
Okay, so that's the nuts and bolts of how it works, but let's just pull back for a second and think about the big picture. Why does this all matter so much? Because the power of the sun is a total game changer. For one, it's renewable. I mean, the sun isn't going anywhere for the next 5 billion years or so. It's also incredibly clean. Making electricity this way creates zero emissions. And it's so accessible. You can put panels on your own roof or build massive solar farms out in the desert to power whole cities. It just works.
But here's the final thought, and it's a bit of a mind bender. Think about that single photon that hit your solar panel. Its journey didn't start 8 minutes ago. The energy that it's carrying was actually born in the fiery heart of the sun, maybe millions of years ago, in a nuclear fusion reaction.
So that little speck of light bounced around inside the sun for eons just to get out. Then it made the 8-minute sprint across the vast, empty darkness of space. And its entire cosmic journey ended when it slammed into a tiny piece of silicon on a roof, all just to become a little spark of electricity. It kind of makes you wonder, right? The answer to one of our biggest problems has literally been shining down on our heads this whole time. What other incredible secrets of the universe are just hiding in plain sight, waiting for us to figure them out?